Hello, everyone. I'm very proud to be here today to present our work, reducing the latency of touch tracking on ad hoc surfaces. Touch interactions are now ubiquitous, thanks to the prevalence of our smartphone. However, touch interactions are still largely confined to small devices. Enabling touch on larger scale ad hoc surfaces can greatly contribute to the convenience of interacting with augmented reality. But the current methods suffer from low touch detection accuracy and high latency. Today, we are going to present our work on solving these issues. The presentation is divided into 6 sections. I'll first go through previous efforts on this problem, followed by the details of our approach. I'll also show a comparison between the results from our work and others. At the end, I'll talk about the limitation of the system. So this very minute, let's move into related works. For previous works, there are methods detecting touch by applying sensors, such as acoustic microphone on users' hands and surfaces. But more directly related to our techniques are the system which employs cameras for touch sensing. Here is one method using the color changes on users' fingernail to detect pressing. Another work here uses the convergence of shadows to identify touch. But both of them highly rely on environment lighting conditions. Some other methods use temperature camera to capture the heat residual left on the surfaces. The problem is it can only detect touch after users remove their fingers, which implies a huge latency. The mainstream methods these days are based on depth cameras. Due to the well-known multipath interference problem of the depth camera, detecting touch location is not always accurate. This technical difficulty is solved by direct with the methods of fusing IR and depth images together. But how to directly detect the touch events moment haven't been well studied yet. Most of the works either uses a single threshold above the surface after counting the thickness of the finger to identify the touch moment, or a pair of thresholds with hysteresis to reduce the effect of noise. Our work is about to improve these methods. Latency is also a critical factor on touch sensing techniques. Many research works investigate on how to reduce it. Hachitech uses a 2-layer photosensor-based structure to measure the velocity of the finger when it comes close to the surface, enabling the system to predict touch events before touch physically happens. Some other researchers stick special vision trackers on users' finger to explore the possibility of predicting touch using the finger's trajectory. The main idea behind our work is to include dynamic information to identify the touch moments. As we all know, when the fingertip hits a surface, its position, velocity, and acceleration changes dramatically. We believe using this representation can help us with improving touch detection accuracy and reducing latency. To capture this representation, we decided to use a data-driven approach. Since there is no existing public dataset available, the first step is to collect the data. The setup is using a depth camera to record participants typing on an iPad, which is covered by a piece of paper to simulate an ordinary surface. On the iPad, we run a full-screen application which records the touch interactions with a timestamp and turns the screen to black on each touch for synchronization. We hired 16 participants with different skin colors to record typing data with different conditions. 2,400 taps were performed per person. To better simulate different typing conditions, we set 3 variables: different typing speed, different finger lifting height, and different finger touching angle. The dataset is released for future research use. This is the big picture of our system. It takes a short series of IR and depth images as the inputs, then goes through 3 stages. The first one is an algorithm extracting depth profile from the fingertip of the input images. The depth profile is passed to the second stage, which is a classification neural network. The current and past output of the network is collected by a tunable heuristic model to identify touch events. I'll talk about them one by one. In the first stage, the goal is to find the depth of user's fingertip through the input images. We use a method similar to direct. At the beginning, before user interacts with the system, we collect the background pixel values for 2 seconds. Then we zero out pixels differ from the average background within 2 standard deviation, which is 95% confidence level. We can get the background removed depth and IR images. Then they are used to generate binary masks, which can be fused together with bitwise OR to get the mask of the hand. Then we find the furthest area from the wrist and assume that's the location of the fingertip. The mask is applied back to the depth image to calculate the average depth of the fingertip. The calculated depth profile will be used as the input for the next stage. The second stage is a classification network. In this section, we'll talk about how the training data is prepared, how labeling is performed, and our model selection choice. As introduced in the setup section, we run a full-screen application on the iPad. It records the touch interactions with a timestamp and turns the screen to black. The color changes can be used to synchronize the video data with the timestamp on the app touching data, which unlocks the possibility of labeling the data automatically. Then how to label the data exactly. The most trivial method is labeling as touchdown, touch up, and non-touch. But then there will be a lot more non-touch labels than touch events, which results a very imbalanced dataset. So we decided to take another approach. We labeled the data according to temporal difference to the touch events. We labeled 9 frames around the touchdown events and 5 frames around the touch up. The number here indicates the sequential relationship. For example, frame before and after the actual touchdown gets labeled as 6 and 8, respectively. 2 frames earlier than the touchdown gets a label of 5. There are mainly 2 benefits for using this. If the exact touch event's label is mispredicted, the sequential labeling scheme gives us a chance to correct it. For example, instead of seeing a 7, we see a 8 following 6. We can infer that there is a touchdown happened. The second reason is it also gives us the ability for predicting touchdown events. I'll talk about this in the heuristic model section. When it comes to what model should we use, we test a variety of machine learning models, including neural network SVM, RNN, and LSTM. It turns out there is no major performance differences. Since we need to build a real-time system, we choose the simplest model, the neural network. The input to the model is extracted a depth profile in the last 5 frames of the images, and the output are the labels. The next question is how to interpret those labels. This is the reason why we have the heuristic model. This is a small state machine collecting predicted labels from classification model and output touch events. The heuristic we set is either seeing the exact touchdown label 7 or 6 followed by 8 or 5 followed by 8. To enable prediction, we can just shift all the heuristic left by an integer n. The larger number we shift, the more aggressive the prediction will be. Before showing the result, let me reintroduce the comparison models we used. As I mentioned before, most of the works uses either one single threshold above the surface to identify the touch, or a pair of thresholds to debounce. To compare with our results, we built both of them and ran a grid search through our data to find the best threshold for each of them. For the results, our basic heuristic model and -1 frame prediction achieved a higher touchdown and touch-up accuracy than both of the thresholds and hysteresis methods in terms of F-score. The column here, the negative latency, means how much earlier the system gives a touch prediction than the ground truth in terms of frame numbers and milliseconds. If we compare between different heuristic models, we can see a trade-off between latency reducing and the detection accuracy. Overall speaking, the system can greatly reduce the latency with acceptable accuracy trade-off. We used the -3 prediction heuristics to build a real-time system to test the system's latency, reducing capability in real life. The result is shown here. Our system can greatly reduce the latency on touch comparing with the previous methods. For the limitation, the system requires a surface which have a different IR profile than human skin to extract fingertip from the user. Luckily, most of daily surfaces materials works, such as wood, normal wallpaper, drywall painted walls, but some other material, like vinyl, may affect the accuracy. Another limitation is that all the experiments are done with consistent indoor lighting conditions. Varying light condition is not tested in this work. However, since this work doesn't use any RGB images, ideally, we don't think it will affect the result a lot. One difficulty of the project is on detecting small motion touches. Some participants only lift their finger up the surface for 5 to 7 millimeters. Any noise on recognizing the fingertip location can easily disrupt the measurements. In the future, use a CNN-based model to directly classify the image sequence may help with the noise robustness. In conclusion, today we presented a depth camera-based ad-hoc surfaces real-time touch sensing system. The pipeline we proposed utilized dynamic information of user's fingertip. The system shows the state-of-the-art touch detection accuracy, while providing the option of reducing latency with acceptable accuracy trade-offs. We also released the dataset for the future research use. Thank you for listening.